All right, welcome to day 4. So before we move on to new material, Ken did some research on one of our questions from yesterday about why we were getting BAM files of different sizes. Well, Ken, do you want to tell them what you found? And actually, I meant to ask you, where did you find the information?
Is that there's different switches in there, different threads and metadata that it's using, and that the collective of all those three results in different sizes that you can get
Yeah, and
nothing you're doing. They said the test that you can do a band compression and no compression.
right. It's really, I had not realized that there's 9 possible levels of compression that BAM can do, that BAM can be in and SAM tools can perform. And it's 0 would be in binary but not compressed, up to 9 being the most compressed. And the reason why there's different levels is it's a bit of trade-off on time versus, full compression, like how much compression you're actually getting. So yeah, so I agree with you. There may be other factors involved, but it looks to me primarily like STAR was using a different level of compression. And then we decompressed it and recompressed it. We were using a different level than the original level so that we got 2 BAM files that were from the identical SAM file, but 2 different sizes. So that was pretty interesting because I didn't realize that there were multiple levels. There are people in Seek Answers or wherever, BioStars, that have the same questions. It's really satisfying when you Google a question and like someone else had it 2 years ago. And I also found, and this is another read the manual moment for me, I was like, wow, STAR has a flag and you can set the compression level of the BAM file. So when you're running STAR, you can say if you wanted to spend the extra time to go for the high level of compression, use whatever the default is, or go for kind of a lower level of compression that might be a bit faster. So yeah, that's STAR manual. It's deep. There's a lot of flags in there. But that one was on, I think it was on page 23 if you want to look at it. So yeah, so that was really cool. Good find. Let me find the PowerPoint. I talked just a little bit about counting reads and also about reproducibility. And today we're going to start doing a little bit of learning about scripting. Okay, so we've done read mapping. We cleaned up our reads. We made sure they were high quality. We mapped them back to our reference genome. And next, we have what is seemingly an easy step, which is to count the number of reads for each gene. So maybe gene A has 100 reads, maybe gene B has 1,000 reads. That's going to eventually, once we do some normalization and statistics, that's going to become our gene quantification values. But right now, all we have is this, where we have all of these reads and we know where they are in relationship to our annotated genes. So for example here, and I haven't sat down and counted all of these little black boxes, but maybe we could say this is about 100 reads that have been mapped to this gene. It looks like some exons are more highly expressed than others, possible evidence of alternative splicing. For our purposes, we're going to count at the gene level and not worry about that. And you can see we've got reads that are split across exons, so we'll need to deal with that. And we got some reads mapping to introns. And whether or not we count those is an additional question, open question. The software that we're going to use to do this is called HTSeq. HTSeq is actually, it's a Python framework. It's this whole really nice Python package that has lots of useful functions to work with high throughput sequencing data. It would require you to know some basic Python programming to use it. But for our purposes, it comes with some pre-written scripts, including the one we're going to use called HTC count. And that is a script that the authors of this package went ahead and wrote and provide with the software package specifically to count aligned RNA reads to a genome. It's pretty flexible. It allows users to select from a number of different counting strategies that I'll show you in just a minute. And you can also select any feature type from a GFF3 file to be the counting unit. So what does that mean? That means we can count at the unit of gene and say how many reads have mapped to this gene versus this other gene. We can count at the unit of exon. So if we wanted to compare each individual exon's expression level, we can do that. Or if you had, those are the only two that really come to mind, is what I would normally be counting. But you can use anything in the GFF3 file to do your counting. It also, at the end of the file, gives you, so it outputs gene A has this many reads, gene B has this many reads, and then at the end it tells you some additional statistics. How many reads were not mapped to a feature? That's generally that they map to the genome, but they map somewhere in an unannotated region. Like there's no evidence that that's a gene in that region. It'll say that it is ambiguous. So this is the stage at which, when we mapped with star, we maintained reads that map to multiple genes. At this point, we are going to throw those out. So HTSeq will tell us, I found this read ambiguous. I found evidence in your BAM file that it's mapped to multiple locations. I'm going to stick it in this category called ambiguous. If it's a low quality mapping, we talked a little bit very briefly about mapping scores. If the read is not aligned at all, so if the read, you know, maybe it was from a bacteria or something, it just did not align to the peach genome. So it'll tell you how many reads fall into that category. And alignment is not unique. Oh, okay, I messed this up. Alignment is not unique is if it's multi-mapped. Is ambiguous is if it maps to two different genes that are actually overlapping. And I can show you, let me show you a picture of that. So here's all the strategies that you can choose from. The first column is the union column, and that's the one that is by default that the software uses. But you can also choose intersection strict or intersection non-empty. In the most straightforward case, you have a read, it maps unambiguously to a single gene. It is always going to count for that gene, no matter which of these strategies you choose. Let's say you have a read that maps to a gene, but half of it is hanging off. It's hanging, we have annotated the genome to say that the gene ends here, but the read actually maps halfway into the annotated gene region and halfway outside of the annotated gene region. In the union scenario, we're going to count that. We're going to say that's reasonable. Maybe this is a misannotation. Maybe this is an unannotated, untranslated region that is actually transcribed. We're going to say, don't worry about that. We're going to map it to gene A. If you selected intersection strict, this would basically get tossed out and not get counted. If the read maps across an intron, again, in the union section, we're going to go ahead and count that. We're going to assume that could be some type of alternative splicing situation that we aren't aware of. But it's from our locus of interest, so we're mapping it to gene A. Again, the more strict definition, if you chose that, would not count that read. If the read is properly spliced as you would expect it against the intron, in all scenarios it counts. And then this is a scenario that you're much more likely to run into with compact genomes, small microbial genomes, although very occasionally I see this in plants, where you have two overlapping genes, usually one on the forward strand, one on the reverse strand. And in this case, if it's really clear that the read maps to one and not the other, you can count it for gene A. But if it maps into a region that is ambiguous, in this case, you can say, okay, the read is largely mapped to gene A, we'll count it as gene A. But in this case, you really can't make a decision. Is that read originating from the forward strand or the reverse strand? This actually can be solved by strand-specific sequencing, but our data is not strand-specific. But now you can order RNA-seq libraries, I think they cost a little more, that tell you if the transcript originated from the forward or reverse strand. So I think some of that ambiguity can be sorted out now, but in our data, we're going to consider that ambiguous. So these are the three strategies you can choose from. Does that make sense? Do you guys have any questions about how to count reads? Yep, go ahead, Ken. So it is part of an independent Python package called htseek. So you can use pip. Have you ever used pip? It's like a Python installer package. Or if you manage your Python environment with Conda, you can use Conda to get it. But it's an independent package. It's easy to find. It's called htseek. Once you import it, it will actually download all of the Python libraries, and it also brings the htseek count script with it. So you don't have to write the script from scratch. It just gets provided with the package. Mm-hmm. Yep, you're going to install the package, install the Python package. And then once you install it, you'll have the specific file that is the script. And when you run the script, Python will be able to find the package you installed and run the script. Yep. Yeah, and so that's basically how it works. So this would be considered, okay, let me go back one. Ambiguous. Yes, that's right. This is ambiguous. Alignment not unique is if you have two genes in different parts of the genome. They are not overlapping, but the read maps equally well to both of them. Or maybe there's 3 or 10 or 50 of those genes. It doesn't matter. Whatever it is, from two or more, if the read maps to those multiple places equally well, it's going to throw the read into this alignment is not unique category. So I always get confused between alignment not unique and ambiguous because they kind of sound the same, but they're actually referring to two different things. So that's pretty much all I'm going to say about counting until we do the lab. So any other questions about read counting? It's not, fortunately, that script makes it really easy.
So for the non-unique, that means that not including multi-copy genes, some genomes have multiple copies.
Yes. So that is a huge problem. If that's what you're interested in, if that's your primary biological interest, are these genes, like one of my students, she has 6 tandemly duplicated genes, and there are regions that are definitely the same amongst them, and like you can't map the reads uniquely. And so if you go back and read that default in our stars paper that Matt was talking about earlier, it talks a little bit about how the failings of current mappers with dealing with that. And the other thing you can think about doing is mapping the reads to that region and then trying to look at it as a region of expression. So combining all the genes as a single count. I've seen people do that. So yeah, it's a tough problem. Any other questions? Okay. I want to talk a little bit about reproducible science and scripting. Reproducibility is becoming a bigger and bigger issue in science these days. And when I say reproducibility, what I mean is the ability to duplicate an entire experiment or a study either by the same researcher or by someone else working independently. I kind of hear reproducibility and replication used interchangeably. I think some people like to call replication or repeatability if you can do it yourself in the same lab again, whereas reproducibility is if someone else can do it in a different lab. And if you can find a biological reality, like this gene is more highly expressed in this gene, and then someone else with completely independent experimental setup, completely independent set of assays, maybe they're even using qPCR instead of RNA-seq, if they can reproduce that result, then you can start having real confidence that it is a biological reality. And this has become a big issue because a lot of scientific papers, when people go back and try to reproduce them, they can't. And that's becoming a really big problem. And there's been called into question a lot of how are they doing their data analysis? Is the data analysis being done in some way that is not proper, that's giving us these unreproducible results? And so I personally have seen a huge rise in the number of reviewers that ask for the exact code that we ran to generate our results. If you try to say, oh, I wrote a Python script, and you say in your methods in-house Python script, they say, oh, well, you're going to need to publish that Python script publicly. We're going to need to see that. Matt recently had a paper from his master's where one of the reviewers went back and tried to completely redo his results and couldn't get the same result, and asked him to really clarify all of his methods from the ground up and repeat them to make sure they were accurate in the paper. So this is becoming, and rightly so, we want our science to be as robust and honest and repeatable as possible. So that's the right reason to do it. If that's not inspirational enough, then your inability to get your data published should be your second level of inspiration. Being able to hand the reviewer every detail of your methods is going to be really helpful, and that includes the bioinformatics analysis. So how do you do this? This requires sharing code, analysis details, and raw data. Data sharing, however, at the peer-reviewed journal level, the journal currently, especially in RNA-seq, is largely only asking for the raw data. So if you're submitting from Nature Genetics or BMC Genomics or whatever you're submitting to, they are going to ask you to put your FASTQ files into NCBI. They're not really going to tell you have to do a whole lot else except do a good job on your methods. Where I'm seeing a lot more detail being requested is the individual reviewers, not the journal. But I can guarantee you the journal will require you to submit your raw data. I've seen there's a lot of panels at conferences and a lot of opinion articles coming out about getting code and analysis sharing required by journals. So while that is currently less standardized, I can guarantee you that is coming soon. People are out there trying to create standards for how to not just submit your raw data, but to submit your full analysis pipeline and hopefully some of your end of your pipeline results as well to a public database. I love all of the Randall Monroe XKCD cartoons, so I put a few in this in this PowerPoint, and this one I like a lot because this guy is getting zapped, and the scientist says, "I guess I shouldn't do that," or a normal person would say, "I guess I shouldn't do that again," and a scientist says, "I wonder if that happens every time. I'm going to do it again." But I like this because sometimes doing reproducible science feels like it's so much extra work and it's so hard, and doing a good job at it really requires you to be passionate about it and to care about this as a topic. But it's possible and it's getting easier. So yeah, to follow up on kind of what is going on in the community right now as far as reproducibility, the FAIR principles were published in 2016 and they have really taken off. And that's an acronym that stands for findable, accessible, interoperable, and reusable. So the new paradigm is that if you are publishing, and especially if you are a publicly funded scientist, your data should be findable by other scientists. They should, if they read your paper, they should be able to go out and find your data. It should be accessible, so it should be easy for them to download, preferably not behind a paywall, not somewhere where they need a username and password that you're not going to send them. It should be interoperable. So that means using peach as an example, if we're sequencing standard cultivars, it's nice if we use those standard cultivar names instead of calling them 1, 2, 3, 4, so that other people working on the same cultivars would be able to compare their data to our data. It also means using the standard peach gene names. So using genes that other people can search and find. If I say, oh, this MLL locus is upregulated, I need to give the official accession from NCBI or the real gene name in a database so they can find it, not just refer to it in some accession that I've made up internal to my lab. And reusable. And that means, maybe somebody wants to do a meta-analysis, compare all of these different data sets from different labs together. For your data to be reusable, it needs to have enough information about what you sequenced, how you sequenced it. If it's an experiment where you're comparing controls and treatments, you should have labeled your raw data controls and treatments so that somebody actually could go back and reuse your data. So these are the principles. It's actually a pretty interesting paper, and there's a whole lot. I like very much just skimmed the surface. There's multiple principles underneath each of these 4 main areas. But that's definitely where science in the United States and Europe and Asia, everybody's really jumping on this and getting excited about it. I also want to talk a little bit about robustness and why we did visualization yesterday. In wet lab experiments, it's often obvious when something fails. It fails because there's some step that doesn't work or some visual way to just see that something has gone wrong. However, this isn't always true with computational analysis. And software is not, sometimes it gives you results and it looks like it didn't fail, but it failed. And you have to go look at your data. And you have to think, does my data make rational sense? And I like to talk about this a little bit with every class because I see a lot of biologists coming from the bench side who just believe whatever a computer tells them. And that's a very dangerous way to live your life because a multi-mapping program, well, let's say a short read mapper program, for example, might map your reads and say, hey, here you go, here's your BAM file. And if you never really look at did it do a good job, you could have a huge problem. For example, Julie had a bunch of data and she mapped it and we were looking at it and she said, you know, it's really weird, Meg, only like 0.5% of the reads mapped. And it took her a few weeks to figure it out. But the collaborator had sent us tomato data, not peach data. It was tomato data. And we're like, well, no wonder tomato data doesn't map to the peach genome. But if we hadn't sat down, like the software ran, it mapped the reads, and it gave her a BAM file. It didn't say, hey, this doesn't look right. It didn't give you some big blaring error. You have to go look at that log, think about, does this make sense? I've got a whole bunch of samples. They all match the peach genome, great. And then I've got a sample that maps at like 0.5%. So it takes actually looking at your data and thinking about it. Also, because I think, you know, this is not Gmail, this is not Google, there's fewer users and fewer bug reports. That means there are real bugs in most computational software packages that you need to be, if something goes wrong, don't be afraid to ask online, try to get a bug sorted out and be on the lookout for them because they do exist. A lot of these software packages are maintained by one lab at one university with a couple of coders. They're just not going to operate like big, robust industry platforms that you expect to never have an error. So really, you need to pay attention to your results and make sure they make sense. On the flip side of that, high-dimensional data is complex and it's difficult to have a priori expectations. So if you can make some, I mean, we could make a judgment call that a peach RNA data set should map at more than 0.5% to the peach genome. So try to set up what a priori expectations can you have, and then go look for them in your data, which can be complex and difficult depending on your data set. Yeah, so always verify in whatever way possible. Look at results at each intermediate step. So it's tempting sometimes when you learn a software pipeline to just run all 6 steps and then look at the data at the end. But generally you can figure out a lot more about your data and make sure that each step is working by looking at the data at each intermediate step. Visualize the output. That's why I like to use IGV. I like to try to, whenever I do read mapping, weird things that you might see in your IGV output. Maybe you see that over half of your reads are mapping to locations without genes. That might raise a red flag in your mind. Maybe the annotation of this genome is wrong. Maybe there's all kinds of things that could be going wrong there. But if you don't look at the output and you don't look at how your reads mapped, you wouldn't necessarily notice that. And also use lots of good controls and examine them in comparison to the treatments when you're looking at your data. So how do you and I do reproducible and robust research? Always do record keeping. Like, I feel like this is hammered in the students' heads from the day they get started about lab notebooks, but then when they get to their data analysis, it's like, oh, that just goes out the window. So definitely you need to be keeping basically a dry lab notebook at all times. So write down every step that you're doing, write down the versions of the software that you're using. I mean, I've had reviewers ask me that and say, well, it's great that you use STAR, but I need to know what version of STAR you used. I need to know every flag you used on the command line. Write simple, clear scripts. So if you are saving your commands and scripts, which we're going to start learning how to do today, write them as simply and clearly as you can. And you can add comments, which is basically, there was this great TA in a class I taught in Michigan. And I don't know if she got this from someone else or if she made it up, but she had this huge slide and all it said was, comments are a love note to your future self. And so if you write things down and then you come back in 6 months or a year, and sometimes, you know, writing a paper, going through the review process, it takes time. You're often going back and looking at this data in 6 months, a year, 2 years. I moved here from South Carolina in 2014, and just last year, somebody was asking me for data and how I did analysis when I was at Clemson like 8 years ago. And I luckily still had it on my laptop, kind of miraculously. So the more notes you take and the more you save, it can really save you down the road. Always save your raw data. Again, a journal is going to require you to upload it somewhere. And publicly release all your raw data and scripts. That's really the new paradigm in science, is not to hold everything closed and not share, is to be as open and transparent as possible. I think we're starting to see a bit of a crisis in public trust of science. When you see Retraction Watch out there, you see all the papers where images have been manipulated. You know, we need to be as transparent and clear as possible about the fact that we as scientists are doing things the right way. We're analyzing data and making it public, and not trying to withhold it and keep it. I mean, unless your lab has IP issues. Like if you are truly seeking intellectual property, that's fine. Maybe you're not going to publicly release your raw data and scripts. But if you're not seeking intellectual property, this is kind of the new way to do things. So yeah, so we're going to write our, well, you guys have kind of been writing scripts already, but we're going to learn how to officially write scripts. So what is a script? I keep saying this word script. It's a computer program, but it's usually, when people say script, I wouldn't say there's this hard and fast definition of what separates a script from a piece of software, but a script is usually small and dedicated to a single task or just a few tasks. So it's something you might whip up in an afternoon while you're doing a data analysis. It's different than someone who's producing a huge software package that they expect to share with the world and have hundreds of users. This is going to be something small, dedicated, but it's going to help automate the execution of tasks. So in other words, a person can run each of these commands one by one, which is what we've been doing in this class so far, and it works fine. However, when you write a script, the commands have been written down and given to the computer to run for you. So it's basically that intermediate step of writing it down in a file and then letting the computer run it instead of typing it directly on the command line. And this also serves as a great form of documentation. Like in my lab, we always keep all of our, if we're going to run an analysis step, put it in a file, save the file, give it to the computer. That text file that has the actual thing that you ran will be there in 6 months. It'll be there in a year. So it's a really good form of documentation. Scripts can be in many different languages. I think traditional, when people think of scripts, they often think of scripting languages like Python and Perl, also R. However, Bash is a scripting language as well. And Nick mentioned this very briefly on the first day, and I don't know how many of you guys caught it, but what we've been using on the terminal is called Bash. So it is a language. What you have been learning in this class, when you type ls, when you type cd, that's a language. And that language is called Bash. And it's called the Born Again shell. The original shell that was written for Linux computers was called the Bourne shell. And then somebody came along and made it a whole lot better, and it became the Born Again shell. So it's kind of a play on words. And it is probably the most popular shell out there right now. There's a number of others, but essentially this is the one that is the most popular, and it runs that terminal program that we are using to talk to the ACF. So when we type things in that terminal, Bash is the language that is interpreting that and making the commands actually happen on the ACF. So shell scripting Bash is it's a simple language. It's not a huge, complex language like I would think of Java or Python. But it's really useful. It's really helpful for doing the type of things we've been learning in this class. So a few more reasons to write scripts. You can customize commands and run software with a few keystrokes. So let's say you want to try to run star, but then you want to add a different flag. Well, you can just go back in and edit your text file, add that flag, and rerun it. You don't have to type all of the other flags and all of the other stuff that you had to type the first time. You're just going to modify, or you just want to tweak one parameter. You tried it with one parameter, you don't like it, you want to tweak it. So it makes it a lot easier to do that. As you learn to scale up, we'll talk about this a lot more tomorrow about the ACF, you can write a single small script and then apply it to hundreds or millions of files. We've seen this with our for loops, where you just run it and it processes all those files automatically. You can also have very modular workflows and components. So you can experiment with different pieces of software at each stage of analysis. Maybe you want to try 3 different mapping programs instead of one, see which one performs better. You can encode all that in a script and run it, and then reuse that script or share it with your lab members. And so overall, scripting, I think, is a really good thing to learn. And this is another cartoon that is a classic for many computer science classes. And people do get really frustrated with the command line, and they think, oh, it's too much effort to learn the command line. It's too hard. It's too confusing. But it's like many skills in science where if you invest the time, it will pay off in the long run. You'll be so much more efficient, so much more powerful. You'll be able to do all different types of analysis. So in my mind, it's definitely worth it. Any questions about reproducibility or scripting?
You know how to use the language. We did find references, and this is because I come from a commercial background and academic background, because I went on the USPTO and did searches in terms of existing patents that were out there and found a number of things that Barry was on railroad because they didn't follow that workflow of being published and being
Yeah, that's a really good point. I have never applied for intellectual property for anything in my lab ever. And so I tend to just ignore it as a source of information. Like I don't ever search patents. I don't ever look for that sort of thing. I also just assume that if a technology has a patent on it, I can't afford it, which is maybe the wrong way to look at things. But that's an excellent point. And there are labs, your lab, Juan Luis's lab, you guys have IP coming out regularly, and so it's a different scenario for you guys and transparency. But for most of us, I don't ever think about it. I'm just like, yeah, here's everything, take it all. I have noticed if you use Google Scholar to search, it brings up US patents. Yeah, they're a little harder to read sometimes. Like you have to get kind of used to the patent language, but it's really interesting if you start digging into them. Yeah. Yeah, you realize that like scientific writing is one style and like legal writing is a completely different style of writing. Yeah. Yep.
In that line of research, meaning that there's a lot of companies that are focused in a particular direction of research, which might be, you might want to parallel in your research.
Yep. Yeah, good point. Any other questions about how to make science reproducible or how to make particularly your computational side reproducible? Okay, so we are gonna start counting reads. So the first thing is to log in as normal. And then I'm gonna go copy that Q sub command. Usually at this point in the course, I have it memorized, but this one is so long, it's not happening. Oh, wait a minute, I'll show you that HT-seq. If you Google HT-seq, it'll give you the main software package as the first result, but the #1 script that people use is this counting reads and features. So if you click on that, that takes you to the actual script that we're gonna be using information about it. You can see the same diagram that apparently has been updated since last time I updated my slides, so I should probably look at that. But this also has all of the flags that you can use. Of interest to us, and these are the different categories I was talking about that it's going to use to tell you the number of reads that don't map to features and why they didn't map to features. How many people managed to get a Q sub to launch? Anyone still waiting? 1 waiting, 2 waiting, 3 waiting. Okay, I'll wait just another minute. And I'm going to go ahead and CD to our course directory. Was everybody able to copy all of the BAM files yesterday? Okay, if there's anyone who does not have the 6 BAM files, put a red sticky up and somebody will come help you. Okay, so yep, always make sure you're in the course folder under your user ID and that you're on a Beacon node. I'm gonna go ahead and clean up my directory just a little bit. We'll actually need all of those BAM files. Let me see. Yeah, keep the BAM files in your directory. I'm going to make a directory called star. Let me move any SAM files that you might have into star. I don't have any SAM files. I thought we created one yesterday. Huh, maybe not. And we did, that's right. That was smart. I got everybody to delete them because they're too big, which is always a good idea because the BAM file has all of the same information, much smaller. See, I forget sometimes. Okay, so and I've moved the log files into the star directory. Again, I just prefer to try to keep files sort of sorted and neat and keep them in little bins where I can figure out what piece of software produced them. But for today's lessons, I'm going to leave those BAM files right here. Okay, so we are going to use HTC count. The command for that is HTC-count. It has lots of different options, as we've seen, just like other command line programs. And then you want to give it your alignment file, which is your BAM file, and your GFF file, so that it knows when it does that read counting, it needs to know where the genes are. Yeah, we're gonna get there. There's just some sort of like stuff at the top to talk through, and then once we start, yeah, no, you're good. The format is the type of alignment file data. So we are going to be telling that it's BAM because that's what we have. You can also use SAM. Sort order, we had told star to give us coordinate sorting instead of name sorting, coordinate sorting. So we'll specify that. You can specify whether or not your data is from a strand-specific assay. So as I mentioned earlier, some RNA-seq library preps now are strand-specific, so you get forward and reverse information. Ours is not, so we're not going to worry about that. We're just going to tell it that it's not stranded. This one is, the type is probably the hardest one to wrap your head around. This is what to count on based on the GFF file. And so you can count at the gene level and say that you want the number of counts per gene. You can count at the mRNA level, which if you were dealing with alternative splicing or you were interested in different transcripts originating from the same locus, you could count on mRNAs, or you could count at the exon level if you were interested in one exon being expressed more highly than another exon. Most typical is gene. And And then you need to specify from your GFF file the attribute to be used as the feature ID. So when you're counting, let's say we want to count at the gene level, we need to specify what parent says which of those exons make up the gene. So it's basically using that parent tag, and it needs to know which GFF attribute to be used as a feature ID. So we'll see that. And there's a lot of reasonably good explanation about that on that webpage I just showed you. If you're using a standard GFF file, the example we show you should work fine. Okay, so let's do module load htseq. And then I'm going to do htseq-count. Our format is BAM. So these flags are a little different than the ones we've seen so far. Well, maybe we have seen an example of this. Sometimes flags have a space and then some more information about that flag. Sometimes instead of a space, they use an equal sign. And you just have to look up the documentation for the software to figure out which kind of style of flag it prefers. Sometimes flags have a single dash, sometimes they have 2 dashes. Sometimes they have both, like you might be able to choose between the short flag -f and the long flag -f format, and they mean the same thing. And then this is just it's very variable across software packages. This is another reason why you just have to go read the manual and look at what they tell you to do. The sort order is by position. And again, we had to look at the manual to figure this out, but they want you to put POS to say that the order is positional. Our data is not stranded, so we're going to say that it's not stranded. We want to count at the gene level. And the ID that we want to use to report those genes is called ID. And that's just from that's one of those tags in our GFF file. And then from there, we can put our BAM file. We also need to tell it where the GFF file is. And then we want to redirect all of the output that htseq is going to produce into a file, and we'll call it 8-400.counts.txt. It's going to give you some, install PySam to spam reader class. Okay, I'm probably not going to work. This worked for me when I tried it a couple days ago. We might just have to convert to SAM for now. Oh, really? How did you load PySam? Is it? Okay. I didn't know they had PySam. Okay, so everybody type module load PySam. Well, one of you guys in the back row edit the wiki and add that module load PySam to the wiki, so anybody following along later, or us when we're teaching this next year, will know to do that. Yeah, this is gonna take a little while. It's a few million reads. any of you guys ever use GitHub? Of course. Yeah, I know. Yeah. So if you guys are going to get into writing scripts and writing code, GitHub's a great place to make your code public. It can be very easy to use if it has a lot of super user, like superpowers, if you're willing to spend time to. But it can be as easy as just uploading your final file. So I recommend it. The whole course is probably know it. I like it enough that, but it's really easy to set up this little wiki that anybody edit and makes it really convenient for teaching. I like it a lot more than Canvas. Is that our new teaching platform? I don't like it. I don't like Canvas at all.
You can get a free like pro account.
Yeah, I know. We're still paying $7 a month. I gotta figure out how to stop doing that. I haven't been able to figure out how to tell them I know you for not making me pay.
Okay.
Yeah, and there's a free version. So 99% of your, unless you're just trying to house a big group and you want to have private repos and stuff, you don't really pay. And like $7 a month isn't that much. So yeah, it's a very convenient little. It's great. Actually, the guy who wrote Linux, Linus Torvalds, it's kind of an interesting story. Unix came out in the 60s and 70s, but it wasn't free. It wasn't open source. And this guy, Linus Torvalds, sat down over Christmas break one year and decided, I'm just going to rewrite Unix from the ground up and make it free for everyone. So he actually wrote Linux, the operating system, and made it completely open source and free, which is amazing. And just a huge gift to the world. And then in the early 2000s, he's like, you know what we need? We need version control software that doesn't suck. So we sat down and he wrote Git, which is like an amazing version control system. And that's like the technology underlying GitHub. So we owe him a lot. Also, I can't imagine being smart enough to sit down and just write an operating system from the ground up at Christmas break. It sounds amazing. A little unattainable. I guess back then it was probably a lot simpler. Okay, so I'm sure some of you are still waiting on your files to finish, which is fine. Let's go ahead and look at this. So if I do an ls, I now have a counts.txt file. And if I do a head on that, I can see that this is a really straightforward, for once, we have an easy, straightforward file format. Yay. It's just a gene name and then number of reads. Nothing complicated about it. Very straightforward. And if you do this for each of your samples, you should have it should make a perfect spreadsheet upload, because even if a gene has 0 reads mapped, it still appears in the file. So all of your files will always have the exact same number of rows. The opposite of head is tail, and that's going to give us the last 10 lines of the file. So let's look at the tail. So at the end is where it sticks these categories of like, how about all of the reads that didn't get mapped to a gene? What happened to them? Well, in our case, we had 125,000 reads that mapped to no feature. So they mapped in between the genes to intergenic regions. If you'll remember, because we used the default union mapping strategy, reads that map to an intron, we counted it for that gene. However, if the gene map's just not at all in the gene region, not in an intron, not in an exon, it kind of falls through the cracks. It gets put in this no feature category. In this case, this is one of those things you want to look at. This is not a very high percentage of my library. We had over 3 million reads and have 125,000 mapping to other locations. That's fine. That's just not a very high percentage. You're keeping most of your data. You're going to get things like this biologically. Regions that are transcribed that haven't been annotated, long non-coding RNAs, RNAs from I don't know, various random transcription sources that maybe you just weren't expecting to see and haven't annotated in your genome. We do have some genes that are ambiguous, which means we must have some overlapping genes somewhere in our genome. I couldn't tell you where, but again, it's a very low percentage. But we have the biggest category. So we don't have any that are too low quality or not aligned. And that's because STAR would not have reported those in our BAM output file. So if you have a read mapper that reports low quality mappings and reads that are not aligned, then you will have reads in that category. In our case, our read mapper didn't report those, so they weren't in our BAM file, so HTSeq didn't find them. The alignment not unique is our biggest category. It's our biggest amount of read loss, and that's actually, I mean, that's almost 1 million reads. That's a lot of reads to lose. But this just goes to show you that genes oftentimes have regions of high similarity with each other, and so if those reads can't be mapped uniquely, for the purposes of this pipeline that we're using, we're going to end up discarding those and not using them. So something to look out for, certainly, especially if you're particularly interested in a region where your gene is highly similar to a lot of other genes. No, so the other strategy that we're not showing in this class, but we do it all the time in my lab, is you take your raw reads and you create a transcriptome assembly. So you assemble your transcripts, or you can download your transcripts if there's a reference genome, and then you just map your reads back to the transcripts and count based on the transcripts instead of counting based on the genome. And you can do that, it works fine. The quality of your transcriptome assembly is going to be the biggest driving factor in how accurate your results are. Yeah. I mean, it has to come from somewhere. It's generally, when you do a transcriptome assembly, you're not getting back full-length transcripts, you're getting back fragments of transcripts. So it's a lot messier. And it's lower resolution than having a nice reference genome, but it's certainly feasible. We've published papers on it. Sometimes you just don't have $200,000 to go out and do a reference genome, and you have to start somewhere. So you can assemble your transcripts. And now with platforms like IsoSeq from PacBio, it's much more feasible to get full-length, high-quality transcripts as a database. And then you can map your reads back to that. You can use the exact same programs that we've used here to map your reads back to a transcript database instead of a genome database. Okay, so now let's talk about scripting. So up to now, we have just been typing things on the command line. We hit enter, we exit at the end of the class, poof, it's gone. If we hadn't written all this down on the wiki, you would probably have no idea what you did or how you did it. And few of our file formats have been really nice, like SAM. It stores the command that was run to build that file. But most files aren't going to do that. Like this file here isn't going to store any information about the program that created it, what version, what flags you use. So it's good for you to be writing that down. So we're going to use the nano text editor. And I'm going to call this file htseq.sh. And by .sh, that's just a suffix. It's giving me a clue that this is an executable bash script. Nano is going to give you a nice blank text editor that you can put information into. I'm going to go ahead and remind myself that I ran the module load htseq command. Oops. I think it was just module load htseq. Yeah, module load Python. And then I'm going to paste the entire command that we used.
Mind if I give a warning about data reproducibility in Nano?
Sure.
It shouldn't be an issue with this script, but with certain scripts, Nano will go up to a certain point, and then it'll stop at the $sign to signify that there's more code after the $sign. When you copy code directly from Nano, it's not going to copy anything past the $sign. I ran into this issue with the undergrads in our lab when they were first starting to use Nano. They would copy over directly from Nano, and it would include the $sign, and when they would attempt to run program after copying it from
I'll show you guys what they look like. Yeah. So see how as I kept typing, it eventually like bumped it to the end of the line and gave me a $sign. And then if you use your mouse to copy and paste, it's only gonna copy the word important. It's not gonna copy all this other stuff I typed. So Nano is not our preferred text editor. It is, however, easy and super easy. Like you can learn it in 5 minutes. BI, Emacs, other text editors are much better. They're not going to give you this sort of like this is just not awesome behavior. But you know, if your line isn't wrapping past the end of the screen, it should be fine.
Yeah, I apologize for the interjection. So
No,
we're
that's
talking
okay.
about data reproducibility.
One of the things we talked about yesterday was the whole approach to documentation. So in this guy, your message 600.
Oh, did it boot you off the key sub? So while we were talking, I just changed this from 8-400 to 8-800 so we can do a different file. We've already done 8-400, so let's do 8-800. Let's do the next file so we can see if it works. So once you're happy with this, you can write out with Control-O. It'll ask you if you're happy with the file name. I'm going to hit Enter because I am. And then Control-X is going to get me out of there. Now if I do an ls, I have an htc.sh script hanging out in that folder. And if I do a cat, which means show me what's in my htc script, it should show me everything I just typed. So we've created a file and we put our command into it. So the way that there are a number of different ways to make files executable. Since we aren't going to fall down the rabbit hole of learning file permissions, we're going to learn a slightly different way of executing. Just to type bash htc.sh. So that is actually, the computer is pulling the text out of the file and running it on the command line as though you had run it, as though you had typed it on the command line. In this case, it's not, it's giving you all of the messages from the software so that you still know what's happening. But now when it's complete, that .sh script still exists in the directory and will be there if you ever need to figure out what you ran. Mm-hmm.
So if you were running like a pipeline of a bunch of different commands, would you recommend you do those individual scripts?
Yeah, if the pipeline is something that we're like developing as we go, I would say we tend to put each command in its own shell script because we're going to end up running it multiple times so we're happy with how it works. And once we have a pipeline that we're really confident, we like how it works, we know what flags we want to use, then you can start just like piling all of the commands into one big file and just running them. And so you can imagine having a script that outputs the QC, does the trimming, does the mapping, does the counting, and does it all in one long script. You walk away from the computer and it's just done really fast. The danger of that is just make sure that you're looking at the intermediate files. And like if something fails, you're like, what step did it fail at? You have to go look at each of the output files to figure out like where did things go wrong. But yeah, it's much more convenient to do it that way over the long term as you get more and more familiar with your software tools and you kind of know what you want to do with them. You can shove all of that in one file. Yeah.
We're actually doing that in Live right now. Pipeline system called Expo. I already written these scripts and I'm using it to individual Expo scripts that I run on large.
Yep. It's also nice because Nextflow is a language that allows you to put in decision points. So it can actually say, if this happens, do this software if this happens to this other software. So it really allows you to scale up and do more sophisticated pipeline development. So working with the Dr. Durrett Smith's lab to develop that pipeline. Good. Did you keep something? Everybody has the, is it the geographic? What did you like to Yeah, I mean, I think we could sort it out if it was just one or if everybody was having the same problem, but the fact that most people aren't having problems.
Because we need the space. It's not based on. Not based on. That's why we looked at
All right, so mine has completed. So while we wait for everyone to complete, I'll just show you this one. So even though I ran it from the script instead of from the command line, it worked just fine. Produced the 800 counts file, which we can check out real quick. So we have our same gene names with different counts. And again, kind of the same ratio of no feature ambiguous and alignment not unique categories. Again, we're probably losing up to like 20% of our data to this alignment not unique category. So that's unfortunate. One of the things that you can do to make your scripts more useful is you can add comments. So I type nano htseq.sh and it just opens this text editor back up. And I can put something on here, like maybe I want to put like running gene counting step of pipeline. And because I put a pound sign or a hashtag, this is funny, I used to teach it as a pound sign and I realized that all the students called it a hashtag. Pound sign / hashtag, if you put that at the very front of the line, it essentially says ignore this line. The computer will ignore the line. It won't try to execute this as a command. So this is how you can put notes back to yourself or to someone else if you want to share this. We might put htseq version is, I'm going to control to write out, control X. 010 was our version. And I'm suspect that I might need to know this for a publication one day. I could add 010 because I can't see when I run HTC count what version it is. It's not obvious to me what version. So this is the type of really good information you might want to give yourself to make sure that you have it when you need it when you're writing your methods. Yep. The computer will ignore new lines as well. So if you put empty lines just to make everything look a little neater and tidier, that's fine. It's not going to bother the execution of the script. It's still going to work just fine. And you can put as many of these lines that begin with the pound sign or the hashtag as you want. You can also put them in the middle of the script. So we might put now on counting. Install or get software. So yeah, you can just add as much in there as you want to kind of make that script as useful to you as possible. And Control O to write out and Control X to exit. Yep. Yep. Yep, that is not a problem. Yeah, you would have to use something like cat. And so you would basically, yeah, you could read in a file. There's a utility to do that. That's not something I do very frequently, but you could do that. Yep. Bash scripting, there are whole books out there on bash scripting. It's very powerful. It's not as big a language as something like Python, but it is quite rich, and there's a lot of things that you can do. So it looks like our for loop is wrong because I altered the whole lesson to use FAM files instead of SAM files, and now it still says SAM. So we can work on writing a better for loop. And I'll kind of show you, again, if you're not quite to the point of wanting to write your own scripts, that's fine. Some of you in here are very new to Linux, that's A-okay. You're welcome to just sit back and enjoy just learning a little bit and not worry about typing all of this. But the way that I would start building a for loop is, okay, I think there's a command in Nano to delete a whole line. Does anybody remember what that command is? Is it Control K? Thank you. Perfect. So I'm just going to delete all of that and get myself a fresh start. I'm going to say for f in star bam. So I'm starting to set up my for loop and to say for all of the files in this directory that end in bam, I want to do something. And I'm just going to give myself the template. I want to put whatever I want to do to each file in between the word do and done. For the for loop to function correctly, for the computer to interpret it, you need to have the for, f, in something, the do, and the done. This is the minimum template that you have to start with to make a for loop work. I'm going to indent this a little just to make it clear everything between the do and the done is going to get executed on each file. And to start, I'm just going to say echo $f. So for me, this is just going to give me confidence that my for loop is operating correctly. This is kind of like building a script iteratively and trying to, instead of trying to write 12 lines of code all at once and then having it fail and having no idea why it failed, I'm going to do something really small and simple and get that working, and then I'll add to it. But for now, let's try this one. I just want to know that it's going to loop over the files, and I'm going to know if it's working because it's going to print the file name out to the command line. So Control O, Control X. I want to write it out. Control X. Okay, and now I can say bash htc.sh. And it prints each of the names of my files out to the command line. So I have confidence that my for loop is working. I can now start adding to this. We have developed this clever little line that uses a bunch of shell functions, bash functions, to extract the name of the sample from the name of the file. So I'll show you, let's see. This is actually the base name $F isn't actually totally necessary, but this saves you down the road if you're using a bunch of scripts, if you're using files that have a path appended to them. So if instead of, let me write that real quick. See how it printed just the names of the files? If it had printed Luster Haven courses, EPP 6, what at 531, M State 1, 10, 400, and it had that whole path appended to it, the base name, what that's going to do is strip off the path. It gives you just the file name. So that's actually, if we ran that, is not going to do anything. So I'll just add the rest of the line. No dot after aligned. Yep, and it's spam. So if somebody, Fong or Julie, if you could update the lesson so that it's accurate, that would be very helpful as we go. So by the end of the day today, when you guys reload the page, the wiki page, it should have the actual accurate code on it. So what we're saying here is this is a regular expression, and it's using a utility called sed. We want to take the part of the name that is aligned.out.bam and replace it with nothing. So that's basically just going to give us back the sample name. This is one of those things where you might copy and paste the script. You don't necessarily want to invest in learning sed or base name. You're just going to learn that if you want to extract the sample name from the rest of the file name, you put all the stuff you don't want in between the forward slashes, and it magically disappears. And eventually, you may be interested in learning how those work because they are both really useful commands. And now if I run it, oh, okay, so why did it give me the exact same output? Any guesses? Well, I think it's giving me the exact same output because I'm echoing the file name. I'm not echoing the base name. So I'm not printing. I don't even know if it's working because I'm not printing it out. I have no idea what it's doing. So I'm going to print it out so I can actually see what I did. So I'm going to print that variable name so I can see if the command is working correctly. In this case, Ryan's right, it is not working because it's printing the same thing twice. So the sed command is not working. And this is very much how scripting works. You write a line of code, it doesn't work. You go back and debug it. You write another line of code, it doesn't work. You go back and debug it. Like, this is coding, this is scripting, this is your life. Okay, so I still think that sed command should work. Why do you think it's not working? Oh, yeah. Okay. So this is a good point. Okay. Let me Control X. So the file names that we actually have are this. And I could even go put that in a comment to make it easier to see. And it's great. You can put a comment in the middle of a for loop. It doesn't matter. So to extract the 10-400, what I actually want to get rid of is all of this stuff. So I want to take all of that stuff and put it in between the slashes. And I'm missing some important bits there. So we're going to add that sorted by chord.out.bam. Align.sorted by chord.out.bam. Okay, so now we can save it, exit. Yay! So now we're printing our file name, and then we're showing how we use that base name and sed command to extract the sample name. Again, like, I don't necessarily expect you guys to leave this class knowing how to do any of this. I just want you to kind of see the power of the command line, and hopefully that will make you more enthusiastic to keep learning about it. But it is something, it is kind of like learning a foreign language. It takes real investment of time, it takes real investment of learning lots of details and practicing. And so, like I said, like, we're not going to really be able to conquer scripting in this class, but if you have a taste for how it works, then yeah, I hope you get excited about it. I also hope that if someone else sends you a script you won't be afraid to start trying to mess with it. Like maybe it's something where you find it on Seek Answers or your collaborator sends it to you and all you need to do is tweak one line to make it work for your problem. If you're not scared of it, if you're like, oh, I've seen this before, I can go in and edit it and run it and just see what happens, then that's going to give you a whole set of new tools that you didn't have before. Okay, so now we have our file name and our base name, and we can actually run htseek. So the format is actually equal to BAM, not SAM. The order is still position. It is still unstranded. We still want to count by gene. Now here's the first place that we're going to do something different. Previously, when we were going file by file, we would type the full command, the full name of the file here. But in this case, we have the file name stored in a variable called $f. So that's actually quite useful. We can just put $f. And this is what is going to make the for loop flexible enough to execute on each and every file. That just means whatever file you're currently looking at, shove the name in here. It goes at this point in the command. Our genome location will not be changing. That will always stay the same, so we don't need a variable for that. And then we're going to call it $base.counts.out. So this is setting up our output file to have our sample name .counts.out. So again, I've done a lot of typing. Is there a typo in here? Quite possibly. The way I'm going to figure that out is to quit and run it and see what kind of errors I get. Or maybe it'll run, who knows? And it likes it. So this is going to go through and process all 6 files. Well, if we wait long enough, which would probably be like 15 minutes, it will go through and process all 6 files one by one. And now you have a script that shows you how to do that. And if you come back later, you can see how you did it. Okay, you guys don't have to do all of that if you don't want to. Again, it's just to kind of show you where you're headed. Like maybe in a few years, this is where you'll be. Or maybe you're in a lab where you need to be there in a month or 2, you know, or maybe you're already there. It's just depending on kind of the culture of your lab and what you're gonna need to do and how much of this you're gonna learn. But it is really powerful. Another motivational fact is that I think biologists who are able to script and who are able to process data on the command line are able to find postdocs and jobs more quickly, and they're able to get paid more. The industry is currently really investing in this type of skill because the data sets are getting so big. So I would encourage you to really think about digging in and trying to learn how to get good at this stuff. I've had 2 people leave my lab and get jobs making more money than I make. So I think that's a very encouraging sign for computational biology. One of them, I told him if I don't get tenure, he has to hire me. He rolled his eyes, but I was not joking. So it's definitely an industry that's growing, and I think that highlights the importance of computation to biology right now. So it's a good area to be in. So don't be intimidated, just try to stick with it and be patient. And you can always come talk to my lab or me if you have problems. We have a revolving door of students in our lab sometimes, people who come ask for help, and none of us mind helping. And Matt, like most of his position is funded out of the dean's office just to help other people with their code and help other people with their pipelines. So be sure to, you know, don't be afraid to come ask us for help. We're happy to do it. Okay, so I am going to let that run because I need to actually have these count files for tomorrow, but I'll put them somewhere that you can all access them. So don't worry about it if you didn't write the whole script. Okay, it's 10:30. Let's take about a 10-minute break. Let's come back at 10:30. That's 8 minutes, and then we'll start on transcriptome project design. Any questions while we wait? Right. Fun stuff.
So if a reviewer asks to see, like, you make in-house scripts, how much do you have to worry that they're something that someone else can just use as another whole path? Your own.
Oh, like security wise?
Not even security-wise, storing.
I mean, I definitely think it's super nice when people publish scripts that are very generic and they utilize command line flags to accept the location of files and sanitize, like strip off the path. But I'm happy if they provide anything that has full paths embedded in it, because at least I can see the command they run and the flags they use, and if they did anything weird that I'm not expecting. I may not be able to reuse that script directly, but I can at least work through it.
I can see what set up things just so somebody else can
Yeah.
That might
Yeah,
take a while.
and that's a huge problem. Galaxy, I don't know if you've ever used Galaxy command line. They're kind of maybe working able to spit out these reproducible workflows. You click the button, you have an accession number on your workflow, and you can go look at it and run it. But considering most of us don't use Galaxy, that might be useful. But that's kind of the optimal world, right? Where anybody can go find in their workflows. We're just not there yet. Maybe in 10 years. Maybe not, I don't know. This is what happens when I take things. Oh yeah, my phone.
Yeah. Yeah, it's right, send it off. Like, yeah, and let it to women. Even those have 24 hours.
Yeah.
24 hours is way better than an hour. Yeah. Yeah, you'll get that from the executive. We've probably been getting when you get to come.
Yeah, we did.
Yeah, email. So, and that'll go through a lot of there's okay documentation in the PDF website. Google or there's all of them. Like, it's almost every tons of universities use it. Tons of other yeah, it's totally fixed. You can email Nick, and we've never been successful with that. But he's basically told me about it. Really important to a monster and I have inquired about we want to go use this. I think the door is open. I don't know how easy it is to get through the door. The door is open to requests like that. I just got things that I know. Yeah, and ours probably debugging you is meant for debugging code or if you're just testing software. It's meant to be a queue where you're for the rest of the computational, the rest of the years of research on software.
Always make sure copy code somewhere. It makes very good copy. Always make sure.
All right, now I'm going to talk a little bit about project design. And I used to talk about this at the very beginning of the course, but I think some of this makes more sense and resonates a little bit more after you've seen some of the pipeline and seen some of the software. So I'm going to talk mostly about how to design an experiment for gene expression quantification, which is probably the most common experimental goal for RNA-seq. However, I'll make a few comments on other reasons you might be doing RNA-seq later. One limitation I want to point out that when you're designing your experiment, you need to be cognizant of this. RNA-seq really gives you relative abundance only. It's not great at giving you absolute quantities of expression. It is not like qPCR. It is, and I'm trying to think of the best way to think about this. How many of you guys have been to like a Chuck E. Cheese or a McDonald's that has a ball pit? There's like thousands of different colored balls. And this is very much like an RNA-seq experiment where you're asking, are there more red balls than blue balls? Well, you can't count every ball in the ball pit. So you're going to take a sample. You might take a sample of 100 balls. You might take a sample of 1,000 balls. You hope that it's a pretty random sample. And you count and you get the ratio of red balls to blue balls. But if you don't know the total number of balls, it's really hard to extrapolate the total expression. So really what you're getting is relative quantities. You're getting how much is gene A in my first sample compared to gene A from my second sample. What you're not really going to be good at getting is how much is gene A more highly expressed than gene B in the same sample. And that's just because transcripts have different biases, like some don't prime as easily as others. That could be that random hexamer binding that isn't really that random. PCR has biases. A lot of that comes from that multi-map to read problem. Some genes have regions where reads just aren't ever going to be counted because they're similar to regions of other genes. So it's really hard to say, well, is the absolute expression of this gene similar to the absolute expression of this other gene? Well, one has multi-mapping reads that are getting tossed out and one doesn't. But you can kind of avoid this mess if the only question you ever ask is, what is this gene doing between my two samples? So you're trying to compare apples to apples. So gene A, if it has multi-mapped reads in sample 1, it's going to have multi-mapped reads in sample 2. So if your experimental question is gene A up or down regulated due to my treatment, you're good. If your question is gene A expressed more highly than gene B, you're potentially going to be running into problems. And if that's really what you want to ask, follow up with qPCR is my recommendation. And there are some ways. I talked about 5x spike-in really briefly before. You can do some spike-ins. You can try to do some absolute quantification. But in general, that's more dangerous with RNA-seq than just asking, is this gene changing between two samples? So I'm going to go through the 3 major considerations for project design. Read count, replicates, and cost. Of course, if you don't consider cost, then that's not a very realistic look at project design. So that is a critical component. I'm going to recommend also that you find a statistician to help you. On the ag campus, we have Dr. Schneider in animal science. She's a statistics. She does like I do bioinformatics consulting. She does statistical consulting. So she actually has a website. She's a very brave woman. She puts her calendar online, and you can just add yourself to her calendar, which I think is amazing. I'm like, oh, that's terrifying. So Tuesday, Wednesday, Thursday, she just has these open blocks of time, and anybody can sign themselves up to go meet with her. But she's a great person to know. And before you ever sit down and plan a project, and goodness only knows, start running the project and getting RNA-seq data back, I would go talk to her first and make sure especially if it's a complicated experimental design, if you've got like split blocks or many factors or whatever, go talk to somebody and make sure that you're doing it properly and that you don't have any confounding variables. If you're not on the ag campus, there's also, or even if you're on that campus, there is a UTK-wide statistical consulting service. It's run, I think you can find it on the library website. Dr. Minchin from the statistics department runs that, and he has a number of full-time employees that you can meet with, and they will come over to the ag campus to meet with you in Pendergrass, or they can meet with you in the library in Hodges. So both of those are really good resources that you should definitely think about utilizing, and maybe bring a cup of coffee and tell your local statistician you appreciate them because they work hard. Okay, so next I'm going to talk about replicates. Replication is really critical in science, and hopefully all of you have had some statistics as undergrads or as graduate students. The more statistics, the better, to be honest. But one of the things that we need to really think about in biology is replication. Biology tends to be very noisy. We tend to have a lot of variables that are difficult to control depending on what you're asking. And replication is really going to help you get your arms around that variation, be able to quantify it, and be able to say that what you're seeing in your data is real and not due to random noise. There's 2 types of replicates that we would generally think about. One is biological replicates, which is where you have independent biological samples processed separately. In the case of RNA-seq, you would want them barcoded. You want to not pull that RNA and sequence a single batch of RNA. You want to have an independent RNA sample from each and every biological replicate. That's in contrast to technical replicates, which is if you did independent library construction or sequencing of the same biological sample on 2 different instruments, or 2 different, you're trying to look for variation in some other part of the pipeline, not from the biology, but from some other part of your molecular techniques. The good news for RNA-seq is that technical reproducibility is extremely high. We have numerous publications in the literature pointing to the fact that if you do technical replicates, they have very little variation. However, as biologists, the bad news is biological variation is often huge. And so really where you want to focus all of your time and money is on biological replicates. I would say don't even bother with technical replicates unless that's part of your question, unless that's really what you're trying to deduce the difference in library preparation kits. Do they introduce bias or something? That would be a different situation. But in general, we work with plants, but I think this translates pretty well to most biological systems. Biological variation is what you want to look at. So in the data set that we were just processing, we had 3 biological replicates. So we had the exact same genotype of peach tree It had been grafted and made into 3 identical clonal trees. And we were taking bud samples from each of those trees independently to see what was our biological variation over the course of the winter between these 3 genetically identical trees. You're not always going to have such a nice system. Maybe you can't get exact clonal replicates. Maybe they're just the same cultivar, but there's some variation. So those are things to think about when you're trying to figure out how similar can I make my biological replicates to each other. Sometimes there's limitations. So how many replicates do I need? That's, I get this question all the time. So the answer is not always super clear. If you only have 1 rep and N of 1 is no longer publishable, well, maybe in a very low tier journal. You're not going to get into most good journals without biological replicates. So answer 1 is you need some. So originally people were kind of saying 10 million reads was a really good cutoff point to provide. Once you sequence an individual sample up to 10 million reads, you're going to get more statistical power by moving on to another biological replicate. So the depth of the sequencing can make a difference there. I still see a lot of publications coming out with 3 replicates. I don't know how long that'll last. Sequencing is still, in the scheme of things, pretty expensive. So 3 replicates is probably going to be okay for a while. But the science says that if you can afford more replicates, you probably should do them. This was a really interesting paper where they just went really down the rabbit hole and they did 48 replicates just to ask the question of how many replicates, when do you actually get diminishing returns? And this is the result, and it's terrifying if you only have 3 replicates. With 3 biological replicates, 9 of the 11 tools evaluated found only 20 to 40% of the significantly differentially expressed genes identified with the full set of 42 clean replicates. So what this means is that if you're only using 3 biological replicates, you're finding only 20 to 40% of the results that are biologically real. So very small percentage of what's actually going on in the tissues or in the cells are able to be identified. Overall, from their discussion, they conclude that at least 6 biological replicates should be used, rising to at least 12 when it is important to identify significantly differentially expressed genes for all fold changes. So if you're looking for very tiny fold changes, very slight up or down regulation, you need 12 replicates. If you're looking for big fold changes and you just want to get the majority of those, 6 biological replicates. This is a yeast study. Does this translate to your system? Well, if you're not working on yeast, maybe not. But we don't have many studies with this depth of replication, so it's one of the few that you can really kind of extract some take-home messages from. They do recommend using EdgeR or DESeq2 as the leading tools to do your statistics. And so in this class, we'll be using DESeq2. There are a whole bunch of tools out there. But I did want to point out that at least a few papers I've seen have really encouraged me that DESeq2 or EdgeR is the way to go. Yep, so this was another really interesting paper. We have the number, for the first chart, we have the number of differentially expressed genes that were detected and the number of reads. And then I have to assume this was to avoid paying color charges, but instead of using colors, they've used like thickness of the line to indicate the number of reps. So when you only have 2 biological replicates, you can see like in the scheme of things, you're getting very few differentially expressed genes. Even as you sequence deeper, you're getting more differentially expressed genes, but the addition of a single replicate, even at a very low number of reads, is giving you more information. You are getting more statistically significant differentially expressed genes. And so basically what this tells me is that the addition of a biological replicate gives you better information than sequencing deeper. A lot of people say, oh, I'll just sequence my samples deeper. That's going to fix my problem. That is not a good trade-off for a real biological replicate. Over here, they're looking at just the power of the study. And again, you see a similar trend where if you have a low number of reps, your power, even with increasing number of reads, your power is very low. So your power to detect true positives is not good. As you add replicates, the power just gets better and better and better. And this paper actually kind of came up with the same conclusion, which is 6 reps relatively deeply sequenced is really where you want to be really accurate. Again, I don't see a lot of papers coming out with 6 replicates because people are always, and we fall prey to this too, where you want to put a bunch of different factors in your experiment. You want to test different times and different cultivars and different locations. And every time you add a factor, you're multiplying the number of samples you need. And then you give up on biological replicates. And it's a very dangerous trap to fall into. If you ask simpler questions with fewer factors in your experiment and you can afford more biological replicates, your data is going to be better. You're going to have more actual sensitivity to detect biological reality. So if you're choosing between EdgeR and DE-seq, this is from Seek Anders. I ran across this and I thought it was worth pointing out. Simon Anders is, he is one of the authors of DE-seq, and DE-seq 2 would be the follow-up to DE-seq. And he said, of course, we like to claim that DE-seq is better than EdgeR, and for only 2 or 3 replicates, I do think it is, but for 5 or more replicates, EdgeR's moderation feature really pays off. So if you are in a lab and you can afford 5 or 6 replicates, I would tend to agree with him that moving to EdgeR is better. If you have 1 or 2 replicates, DE-seq 2 is probably not going to give you any statistical significance. It's just going to say, nope, I refuse to accept that your data can produce statistically significant genes. So in that case, a lot of people, 1 or 2 biological replicates, they move to EdgeR. EdgeR gives them results. I would find those results to be highly questionable. People do it, they publish with it. But my recommendation is DE-seq at low replication, EdgeR at high replication. And if you just don't have enough biological replicates to get statistically significant results, try to go out and get the biological replicates because that's going to give you a real answer. Very few. Very, very few. Yeah. It's but prices are coming down. It's getting easier. You know, we've gone from paying $400 an RNA-seq library to more like $200 just in the past 4 or 5 years. So the prices have gone down by half. I don't think they're going to go down anymore. I think we're kind of at a plateau until a new sequencing technology comes out. Well, I've heard that the next big advance in RNA-seq is not going to be on the sequencing side. It's going to be on the library prep side. The library preps are going to drop from $150 to $30. However, I've been hearing that for 3 years and it hasn't actually happened. And I don't have a good enough understanding of what they're working on in the library prep side to make it that much more efficient. But somebody from a core facility in Texas told me that, and I keep calling him and he keeps saying, well, not yet.
Is the main effect of not using this recommended amount of false negatives?
Yeah. Well, yeah, true. You get a lot of genes that are probably significant that you're just not going to pick on as significant. But you do get, you get both type 1 and type 2 error, I think, which is scary, right? Because you're getting both types of error. So you could potentially be basing your research program on chasing genes that aren't real. Because when you have very low biological replicates, we end up doing a lot of massaging to estimate biological variability. And if you don't have enough replicates, it can often be estimated to be too low, which means that you think things are real that aren't real. Or if they actually have a legitimately small fold change, you can't find statistical significance for it. So yeah, you get both types of error. It's this problem. Lots of people like to pool their samples. So I had 6 individuals in my experiment. I extracted RNA and I put it all in the same tube and sequenced it with a single barcode. And this is also a really big problem. People say, oh, well, the genes, the transcript expression level averaged out. The average is fine, it's accurate. And that's true, you are getting an accurate mean of the number of transcripts across your samples, but what you're not measuring is biological variability, which is really what is probably causing more noise in your experiment than anything else. So some people are still publishing with pooled samples, but it doesn't really make any solid statistical sense to do it this way. And yeah, you have low positive predictive values, and I don't recommend it. And yes, it sucks to pay the extra money to do all these extra library preps, but it's really the only way to go if you want solid data. I want to talk a little bit about blocking, which hopefully most of you have had some experimental design before now, and this shouldn't be too unfamiliar. But when you're setting up an experiment, you often want to do randomized block design. That's the typical approach. You divide your samples into blocks in order to control variation between the blocks and randomize assignment of those samples to the blocks. This all sounds familiar, right? Everybody feels pretty good about that? Okay. On the sequencing side, you can also have blocking effects that you need to worry about. I think this is becoming less of a problem over time. Illumina is very robust. I don't see as many bad lanes as we used to 5 or 10 years ago, but it still happens. And this is a cautionary tale from, I think, about 4 years ago, where this really great high impact paper comes out comparing the transcriptional landscape between human and mouse tissues. And then somebody else, Gilad and Mizrahi Man, came out and basically said this entire paper needs to be retracted. It is totally flawed because they didn't do proper blocking. And this is what they did. So they took each of their samples. No, this is the confounded design. This is what the paper did, the first paper. They took each of their samples and they sampled them on individual lanes. And actually what they did is they put all of the human samples on one lane and all of the mouse samples on another lane. And it turned out that there was some intrinsic failures and some really bad data processing that went on in one of the lanes and not the other. So all of their statistical significance between the human and the mouse was completely due to technical artifact and not due to biological reality. And they got kind of dragged through the Twitterverse and torn apart for being bad statisticians and bad scientists. So I think it's a really good cautionary tale that that's not what you want to do. However many lanes you're going to do, take each of your libraries, pool them, and split them across all of the lanes. So if you have some terrible technical failure on lane 2, it's not going to be confounded with all of the samples that were run solely on lane 2. Most people don't do this, but you should. Talk to your sequencing facility and make sure, because a lot of times you just send your sample off and you don't necessarily know how they're splitting it up. Are they on the same lane or on the different lanes, whatever. So definitely want to talk to your sequence facility. This is a public figure. You can give them this figure and be like, don't do this, do this, just to make sure. So, and I think it's just an important part more globally. When you think about blocking, a lot of people just think about it at the initial, like I'm growing some plants or I've got some microbes in petri dishes, and they think about blocking there, but they don't think about blocking all the way through the experiment. So try to think about where could bias or failure creep in at any technical part of my experiment, and can I block my way out of that ruining my experiment? Okay, so we've talked a little bit about replicates, 3 at a minimum, 6 if you can afford it. Now I want to talk about read count. We kind of saw a little bit from the previous slides that people kind of coalescing around 10 to 20 million reads as the minimum number of reads you want per sample. Again, this is going to kind of depend on the complexity of your organism. That's a eukaryotic sample. If you're working with a microbe that has 5,000 genes instead of 25,000 genes, you might need less coverage. The ENCODE consortium did a really deep dive on the statistics of RNA-seq and what you really need to do to get solid results. They went all the way up to recommending 30 million reads per sample. And if you're trying to be extremely precise and look at lowly expressed transcripts, 100 to 200 million reads per sample. However, there's definitely some debate in the literature about this. This paper said as low as 1 million reads can provide the same sequencing accuracy as greater than 30 million reads, but this paper was very much expressed only on highly expressed genes. So this very much depends on if you're looking for like a global overview of gene expression, or if you're really concerned with particular genes, especially if those genes are lowly expressed. Here's another paper. Beyond a depth of 10 million reads, replicates provide more statistical power than depth for detecting differential gene expression. So if you're trying to debate between buying another lane that's going to give you more depth versus buying a few more biological replicates, this is the cutoff point where diminishing returns, you might want to go with more biological replicates. Look at what's being published in your community. That's usually a good sign of what is being accepted in the literature. And also look at what resources you have can make a difference. If you have a well-assembled and annotated genome, you can save money by doing single ends and shorter reads, and maybe try to squeeze a few extra biological replicates in that way. If you're doing a de novo transcriptome assembly, you definitely want to focus on getting those longer reads and the paired ends to make your assembly better. So again, if you ever want to come talk to me or any collaborator you have who's a bioinformatician, they can kind of help you make these decisions. Or you can just read the literature and see what other people are doing. It's usually pretty good. Recent literature, of course, don't look at 10 years ago. This field moves fast. Another thing that a lot of people are starting to do to save money and squeeze more biological replicates, and this is also a cheaper library prep, is 3' RNA-seq or 3' tag-seq. And this is, instead of randomly priming and sequencing the entire transcript fragment, you focus all of your sequencing just on the 3' end. So if you lose some data, you're going to lose information about alternative splicing. You're going to lose data about variants that are upstream of your tag site. What you get in return is the same amount of statistical power per gene with fewer actual reads and a much cheaper library prep. So I know there are people in the animal science department doing this for cows and chickens right now, and people starting to do it in plants. And it's kind of an exciting new way to maybe spend less money and get more biological replicates. Does this make sense? Anybody have questions? You're basically just priming and sequencing off of and selecting based on that poly A tail. So you only get the very end of the transcript in your sequencing. You don't get the whole transcript. So instead of getting lots of random reads all over the transcript, what you get back is these 3'. They're always, they'll be different. They can be different lengths, but they'll always be primed off of that 3' end. Yeah, any questions? Yeah, I already said some of these. Requires fewer reads, easier library prep. Single read data is sufficient. You don't need to worry about paired ends. The disadvantage is no transcript splicing information. It only works for eukaryotes because it does depend on that poly A tail. And it's a lot better for organisms with reference genomes. You can find this paper and go read it if you don't have a reference genome and you're interested in trying 3'-seq. I'll talk about cost a little bit. We have public pricing for the UT Genomics Core, but we only have a MiSeq. So you're very limited in your instrument options here. My lab uses the MiSeq for amplicon sequencing. Fong does 16S and ITS sequencing on it. Veronica runs the MiSeq. She's fantastic. She has a ton of experience in amplicon sequencing. It's a great system. We do not run RNA-seq on this system. There's a couple of reasons for that. That lab has very little experience with transcriptome libraries, but more than that, it's too low throughput. Almost all the RNA-seq designs that you want to do need more reads. There's no point in paying. So the advantage of the MiSeq is the longer read length, but it's lower throughput. It's often not worth it. If you're trying to do a really big RNA-seq experiment, it's more cost effective to go to bigger instruments that are more cost effective. These are other places you can go and look for public pricing. Sometimes if I'm just pricing something out for a grant, it's nice to just go look at the prices without having to like call and talk to a person and spend like an hour on the phone. So all of these are places I like to go look at pricing. Yeah, and so again, if you need help, let me know. But this can get really complicated because some Illumina instruments have lanes, some don't have lanes. So the pricing, I think most of these also have like the number, how many reads you should expect to get back per cost per lane. And most of them will have the library preparation cost per sample is a separate price from the lane cost. So you have to pay for somebody to sit at the bench and make your libraries, one for each sample, and then you have to pay for the instrument to run. So don't forget to budget both. Just wanted to make sure that was clear. If you go to something like a company like GeneWiz or Novogene, they'll give you a single price that incorporates library prep and a minimum of 20 million reads. So that's a little bit more convenient if you're writing a grant or trying to price things out. But none of these facilities do that as far as I know. Okay, so a little bit about other projects. Some of the recommendations I think are very different depending on if you're doing something a little bit more difficult or more complicated. There's a great paper, a survey of best practices for RNA-seq data analysis, and they walk you through tons of different pipelines and what types of data that you might want for all different scenarios. But I want to talk briefly about these 3 other types of projects. We do a lot of de novo transcriptome assemblies in my lab. So we are usually looking for 20 to 40 million reads from a single individual. Longer read length is better. This is the one case in which going to a MiSeq might be worth it because you can get longer reads. Paired end is better. You want that length data, you want that pair data. It's going to really help with your assembly. And if you can afford it, you should consider a long read technology because that's going to get you a much, much better assembly. And some people are moving on. For a long time, people were doing long reads and then they mapped the short reads back to the long reads to do error correction. We're seeing a lot more papers coming out with long read only and using the long reads to correct themselves. So interesting new strategy in the transcriptome sequencing world. We recommend doing a single individual if possible. If you try to sequence a bunch of different individuals with a bunch of genetic variation, your assemblies are not going to be as good. However, within that one individual, if you can get many different tissues and developmental stages represented in your RNA sequencing, that's good. Because there's going to be genes that are very specific to certain tissues and they're only turned on at certain developmental stages or in certain tissues. And so to capture as much of your transcriptome as possible, try to get as many tissues and developmental stages as possible. And I put some papers down here if you're interested in this sort of thing. If you're doing genome annotation, sometimes we do RNA sequencing solely to annotate a reference genome. It's really similar advice. Longer read lengths are better, paired end is better, consider a long read technology, and use a single individual. And all that's going to help you to do better annotation of your genome. Alternative splicing, again, I'm just going to say paired end sequencing is the way to go if you're interested in alternative splicing because you need that extra distance information to figure out where new splice sites are, where the splicing is happening, and to do this type of annotation. So a lot of what I said before, you may care less about biological replicates in this case, and you may care more about getting longer reads and more depth on a single individual so that you can detect rare alternative splicing events. So basically, just take everything I said at the beginning with a grain of salt if you aren't doing gene expression. If you aren't doing gene expression, all of those like kind of project design considerations might need to be adjusted. Yeah, so this is just why you really want that paired end data if you're doing isoform variants or alternative splicing, because it's going to help you figure out using those pairs what exons are being skipped, which ones are being included, and where your splice sites are. Okay, so overall, I talked about replicates, more is better, cost, how to find costs and balance cost with replicates, and what kind of read depth. Depending on how much you care about your global gene expression versus very locally expressed genes, anywhere from 10 to 20 million reads, which is typical, up to 100+ million reads per sample. Reading a lot can really help. So read a lot from your community, read a lot of transcriptome papers, and it'll really help you with project design. Any questions about that? No. You guys are so quiet today. No?
A lot of projects I see are using MiSeq. People use MiSeq.
Yeah, we're ordering everything right now from HiSeq or NovaSeq, just because we can do 20 to 30 libraries at a time on a lane, which is really nice. On the MiSeq, you're looking at doing like just a handful. So it scales. If you're doing, because we're usually looking at ordering, like for Gilly's project, how many samples did you have? 90 something? So when you're looking at that many samples, you got to scale up to HiSeq or NovaSeq for it to be affordable. MiSeq is great if you're doing a de novo transcriptome. I will say that, but it's, you know, for some applications. But if you're just trying to get a lot of reads for really cheap, it is not cost effective. It is, Veronica teaches a really nice course where you get to go through all of the stages of preparing a library and running it on the MySeq. And I think even if you're using HiSeq or NovaSeq, it might be worth taking the course because you get to see the instrument, you get to see how library prep works, you get to see how the data analysis, at least the first few stages, are done. So that is really nice. And I think if you enroll in the course, somebody gets free sequencing. Like at least one person gets a couple of free library sequencing, use their DNA as the course for the course students to work on. So that might be a way to get totally free sequencing. I don't know how you get in line for that. I'm sure lots of people want it, but that would be convenient. Any other questions? All right. Okay, now Fong is going to talk about differential gene expression. And assuming we have a little bit of time at the end, I'm going to do a really quick introduction to R.
Okay, I'm going to talk about the differential expression statistic analysis. We're gonna cover 3 parts. I will talk about the first 2 parts, and Meg will talk the last part. By the way, I updated the slides just with one of the slide. And if you download the former version, maybe you want to download the updated version. Okay. So after the HT count, we already generated the count data, which is on the rows, you have all the gene names. On the each column, you have the sample ID, which seems very clear. But when we start to think about, we want to do some statistical analysis. We want to compare if one gene is differentially expressed between treatments, right? So if we say these 3 samples, the first 3 samples, if we say these 3 samples belong to one treatment, these 2 belong to another treatment, can we just do a t-test to test the treatment impacts, do you think? Which we used to do because when we have only one treatment with 2 levels, right? But the assumption is the distribution of the number or the variable is normal distribution, and the variance is consistent between treatment. But this is a problem for most of the RNA-seq data, which is the count data. We have a major problem in terms of the count data. So especially for RNA-seq, in terms of normalization, we have 2 major concerns for differential analysis, differential expression analysis. The first thing, the first concern is the sequencing depth between samples. For example, for sample A, we have this kind of distribution of the reads. For sample B, we have this, like this. So when we compare sample A with sample B, it seems that for each gene, this kind of double express. But in fact, it's because sample A, we had more read depth. So we need to take that into account. Another concern is the mRNA composition. In this case, for sample A, this gene, it eat up most of the reads, right? And this gene is differentially expressed. So when we do the normalization, we need to take into account of both situations. And we have other concerns too for the normalization, which is the different lengths of the transcripts, the different differing ability to measure reads, also some GC bias. But for this purpose, when we do the differential expression analysis between treatment, so these concerns, we can just ignore that, because for the first, for differential length of the transcripts, that is things we needed to take into consideration if we compare gene expression within one sample instead of differential expression analysis. Yeah, but good thing is DSEQ2 now, they have solutions for these other concerns. Yeah. Here I summarize, which I found from other people's GitHub, so I just updated some a little bit here. So now I just listed the pretty common normalization method. For CPM, which is a count per million, it's basically you calculate the relative abundance of each gene within a sample. TPM and RPKM, FPKM, they take into account of the transcript length and also the read depth. But for CPM, TPM, and RPKM or FPKM, they cannot be used. This kind of normalization is not enough for you to do differential expression analysis, because it didn't take into account of the variation between samples. So, but DSEQ2 and HR, they taking into account of the RNA composition. So these two normalization methods can be used to do the differential express analysis. Yeah. In terms of the details, you can just go back and read this slide. I will not talk into much of the details. Here is an example of the normalization for DSEQ package, which is R package. We're gonna use this R package to do our differential expression analysis. So basically, it uses a median or ratio method to do the normalization. Basically, it calculates the scaling factor to take it into account the read depth and also the mRNA composition, which we mentioned the major concerns. For example, we have these many genes in sample A and sample B, and these are the counts from sample A and sample B. What the DSEQ do the normalization is, first it will calculate a pseudo reference sample, and these counts are the geometric mean from each of the sample, and it will calculate all through all the genes, calculate geometric mean, and then it will calculate the ratio between the sample A count versus the reference. So it calculates ratio for each of the gene within a sample. And then similar thing for sample B, they also use the 700 count divided by the 1400, which is the reference count. It has the other ratios. Then the scaling factor is just the median of these ratios. So here we can say this is the ratio is 1, but most of them, but all the remaining, the ratio is 2, right? So we just calculate the median, which gonna be 2 instead of the mean, or and this sample also have the ratio of 1, but most of them have the remaining have the ratio of 0.5. So the scaling factor gonna be the median of all the numbers. It's gonna be 0.5. Yeah.
You mentioned on the pseudo-referencing sample that takes up, which means that there's some sort of distribution of the data.
No, it's like just a geometric mean. So it's the square roots of the when you multiply 2,800 with 700, then you calculate the root of this geometric mean. Anyone knows the term geometric mean? No? Okay, yeah.
It just seems like in normalization, you're trying to get that commonality in general. And one column has to do with means, and then the other one has to do with median.
Yes.
Which would be relative to this.
So the ratio is all calculated in with a reference, with a pseudo reference. The pseudo reference is calculated across all the samples. Yeah. So basically, it's taking into account both the reader depth and also the mRNA composition. If this doesn't make sense, it will not influence your process. The point here is you can trust DSEQ2 for this kind of normalization. Yeah, okay, I'll give if you look at sample A, it's all like 4 times of sample B of the counts, right? But this is kind of an outlier. So the assumption for this normalization is only few of the gene are differential expressed. That's why it uses the median of the ratio. So this is kind of an outlier when it considering the scaling factor.
Even though it's an outlier, you're still figuring it in.
Yeah, we'll still calculate the ratio, but when we do when we calculate the median of the ratio, this is not. Yeah, it will not matter. Yeah, if you have genes extremely expressed or very lowly expressed, I mean, you are taking the ratio or the median of the ratios, so that extremes will not be a matter. Here I'll talk about some challenges and improvements when we do statistical and modeling. The problem for the count data is, I mentioned before, it is not normal distribution, and the variation depend on the means. Also, it has another problem is the sample variation is way higher than the sample mean. The third problem is usually considering the cost, we have only limited replicates, so which make the estimation of the variation very hard. Yeah. So originally, people using Poisson distribution as assumption for the count data, but they found the problem is it predict less variation than what we see in the data, which could lead to the higher false positive. And then people come with a negative binomial distribution, which is a better fit for this kind of RNA count data. And in this figure, you can see the purple color is predicted, the variance predicted by Poisson, and this orange color is use negative binomial, which indicate the Poisson is always less predicted less variation compared with the real variation, which causes a more false positive. And there are a lot more approaches in terms of the assumption of the distribution and also the testing strategy. I mean, there is no like one rule applies for everybody. So you may want to check each of these and looking into the details to make a decision which one you want to use. Here is a summary from this paper. They compared different software packages in terms of how many differential expressed genes they can detect. So when you on the x-axis you have the number of replicates, and on the y-axis is the number of the genes you detected to be differentially expressed. So when you have very few replicates, the results could be varied between softwares. But when you have more replicates, each of the softwares it performs better. In terms of the precision of the softwares, same thing. If you have few replicates, it could be very fast a lot. But when you have a lot more replicates, they performs almost approaching to 1, all approves. So the problem now is basically deal with less replicates. So in terms of which software you're going to choose, here, as we read a paper, you may realize most of the papers use D6-2 and AGR for iron-seq analysis. Yes, one day when we have lots of affordable biological replics, we may just use non-parametric analysis instead of the parametric one. Now I'll talk a little bit of the principles of the D-seq, which we're gonna use for tomorrow's analysis. So for D6-2, it accepts only the wrong count as the input, and it uses the median or ratio to do the normalization. The assumption for the distribution is negative binomial distribution. It uses a generalized linear model to fit each gene, which is very flexible, which allows a very complex design of the experiment. And it uses a wall test to compare, to do the pairwise comparison. And in terms of you have many genes, you wanted to do the p-value adjustment. Here it has the Benjamin Hirschberg, but you can choose other choices too. Yeah, since the I forgot which year it came, the D6, but now it's already updated to D6-2. Along its development, they also have some improvements. One thing is they have the shrinkage for the dispersion estimation. The dispersion estimation is basically they estimate the variation of the genes. So before shrinkage, okay, clear. Okay. Originally, they used a maximum likelihood estimation method to do the dispersion estimation, and they found the variation they estimated is usually very large. So they shrinkage this estimation, use the Bayesian modeling method, which basically shrink the variation. It could increase the power. Another shrinkage is for the log fold change, because the significant tests are usually to be less reliable for the genes with very low count. So they did also the shrinkage for the log fold change. Also use empirical Bayesian modeling method. If we compare before shrinkage, it has a lot of genes being has a higher log fold change when the count is very small. But after shrinkage, this part are just be removed out. Okay, this is just an example how you formula how you do the formula when you do the DSEQ2 analysis. For this experiment, we have two treatment. We have samples from two genotypes, which are sensitive and a resistant genotype to the drought. And the treatment is a drought and a normal water condition. And we put a formula like genotype plus treatment. Here we put the treatment here because we want to see, we want to do the pairwise comparison of between the treatment levels. We put it in the last of the formula. Another thing you may want to take into account is interaction effects. For example, for this is just one gene, and this is a log of the count. So for the sensitive genotype, the expression of this gene just increased, but for the resistant genotype, the expression just decreased. So in this kind of situation, you want to take into account the interaction. You want to know if one treatment will influence the other treatment impacts. And there are a lot more analysis DSEQ can do. You can go to this link to look at their documentation. Okay, Meg will talk about the transcript level quantification. Do you guys have questions? Okay.
Slide where you have the pull up to the sensitive and resistant. There's a correlation analysis of the clusters.
It is just a gene. Just one gene.
Yeah, each gene is treated like an independent experimental unit, right? So you're testing the gene count to your samples.
Okay, so one is positive.
So if you don't take into account the interaction, maybe it's just like this is increased, this is decreased. If you don't take into account the sensitive and resistant, it's just maybe just flat, right?
Okay, when I looked at it, positive.
No. Okay, yeah. Maybe I should use this line, just this two cluster of the samples. Yeah. Yeah. It's kind of misleading. Yeah. Yes.
And I think it's important to point out, like, a lot of this is so complicated. I mean, you should be able to set up your generalized linear model and determine your factors, but under the hood, when we talk about shrinking dispersion and estimating variance, a lot of that is just crazy massaging and totally goes on with biological work. None of that would be necessary if we had all work to do with biological work. So it's something that it can be pretty difficult to dig into. I recommend if you're using these software programs to read papers. But yeah, some of it's quite complicated. And EdgeR has a pretty different normalization scheme. If you're using EdgeR, none of this really applies.
Yeah. And it's always good to consult the statistic experts.
Yeah.
To ask them if what kind of data you have, what kind of software you want to do. Ask them to do that.
Okay, so really quick, I'll talk
talk a little bit about transcript quantification. So this is really a fun new way to analyze your data that's becoming very popular in the RNA-seq world. And essentially, it's looking at trying to quantify expression not at the gene level, but at the individual isoform transcript level. And so I have an example here of the same location in the genome can be transcribed in two different ways. Well, transcribed and processed to result in two different transcripts. So this first one has 3 exons that are the introns, 2 introns are spliced out, and you get one product, maybe under a different condition or in a different developmental stage. You get a different form of splicing, and you get one giant intron spliced out, and these 2 exons end up together and produce a different protein product, right? Like you have real amino acid differences here. So it becomes really interesting to ask the question, and it's been shown in humans, like over 90% of genes have more than one splicing isoform. And that those are really important biologically. That cells do respond by altering the ratio of one isoform to another isoform that's being produced. And so the way we've done the analysis in this course, you wouldn't get any of that data back because we're looking at the gene. We're just saying this locus is being upregulated or downregulated, but we're not looking at what are the specific isoforms coming off of this locus. So a lot of people are really interested in starting to look at this. It's currently pretty highly recommended by a lot of people in the field. We've talked a little bit about multi-mapping transcripts. So this becomes a really huge problem here because if you have, there we go. If you have all of these reads could come from isoform A or B. So how are you going to use them to count? And all of these reads could come from isoform A or B. So you can't really use them to count. The only reads that are helpful are these reads in red that definitely anchor you to isoform A, or these reads in blue, which because of their paired in nature, or because if this is a single read that's split, you can definitely tell they came from isoform B. So you lose a lot of your informative data here, right? Only a much smaller percentage of your reads are going to be informative for differentiating between your isoforms. So there's various ways that people handle this. All of these are software packages that you might want to look at. As you can see, some of them like Salmon and Callisto are quite new. So definitely a new area. But at the end of the day, you can still use DE-seq2 to do your statistics. There was a really interesting paper, the Sonneson paper that came out in 2016, and they recommended, and we haven't started doing this, but what they recommend is doing the transcript level quantification, but then summing it all back up to the gene level for your final reports. And they claim that that gives you a more accurate, powerful, and interpretable level of results, looking at genes instead of transcripts. But the transcript level estimates actually yield more accuracy. You can read the paper. All of this is largely a moot point if you don't have all the isoforms of all your genes annotated in your genome. So for us in the Peach genome, most of our genes don't have a bunch of different annotated isoforms. And so the upfront work to go in and take the RNA-seq data and try to deduce all of the possible splicing formats for every gene is something that we're not going to invest in. So for us, it hasn't made a lot of sense to do this. If you are working in a model organism like human or mouse or fly, it's likely that somebody in your community has already done a lot of the upfront work to go generate the GFF files that will have every single possible isoform of all of your genes. So if you have that, I would say consider doing some reading and considering going down this path. If you don't, maybe don't worry about it. Or if you know that your gene of interest has alternative splicing units, this is a way to get, these are the software packages you can use to get at those and try to figure out isoform differences. Again, that's dependent on if you have a gene and you know it's alternatively spliced that you're interested in. If you have a de novo assembled transcriptome, statistically, this really presents some problems because transcriptome assemblies are rarely very good, especially if they're generated solely from short reads. So a lower percent of your reads can be unambiguously aligned, usually, so you're losing statistical power there. And the adjustment for multiple testing is actually a lot more severe because a lot of times when we do a transcript assembly, we'll get 50, 60, 70,000 transcripts back, when in biological reality, there's only 20 or 30,000 transcripts. So we've got a lot of fragmentation. So a gene will actually be assembled into 2 different pieces instead of 1. So all of this makes everything messier and makes your data less reliable. So if you're in that boat, I want to point you to a package called Corset or RapClust. Actually, both of these work really well. That basically they take all of your little fragmentary transcripts that you assembled and cluster them into the best guess for what is a gene from this organism. And it just really makes your statistics a lot better, and it kind of reduces some of that statistical hit you take from having an inaccurate representation of your transcripts as your quote unquote reference. So again, we're not going to do this in this course, but for those of you who might be doing de novo assemblies, I wanted to point it out. Tons of references. Statistics is hard, but it's a really, really important part of this whole process. So my recommendation is to read up a lot on what you're trying to do, make sure you're doing it right. Any questions?
What percent of breed, is there a percent of breeds below which you would just call data set lost?
Yeah, we had that question with the blueberry data set recently because, I don't know if I would say law. Well, yeah. So I wouldn't say there's a hard and fast cutoff. So there's a couple of questions here. So we did some sequencing of a blueberry species, and there was a reference genome for a different species. And we mapped the reads back, and we were getting like 50 to 60% mapping. And we had this really big debate. Is that good enough? Is using the reference and losing 40% of our data better? Or is it better to try to do a de novo assembly and map our reads back? And we have this whole long paper about that. There it is. Comprehensive evaluation of RNA-seq pipelines in diploid. Maybe it'll load. Anyway, we looked at both a polyploid and a diploid system. And you can go through the whole paper. But Miriam's final conclusion on this is that if you choose to map to a different reference, or if you choose to do your own transcriptome assembly, you're going to get back a lot of the same genes. So it was a bit reassuring at the end of the day that both decisions ended up giving you the same statistically significant genes, which is good. But this is the paper I would recommend you read. If less than half of my data set is mapping back to my reference, then I would get really worried. I mean, preferably, if you're sequencing a species and that exact species has a reference genome, you want to see 90% plus of your reads mapping. They may be multi-mapping, but they're mapping, which is good. But if it's less than 50%, then you're even less than like 75%, you really need to start asking yourself some hard questions about what's going on and why your reads aren't mapping, and if it's better to do a de novo assembly. And yeah. But good question. Any other questions? This is a fun paper. We're about to learn R. So I guess I think it's worth pointing out that all of these diagrams that Miriam did are all like an R, and you can just make these super crazy, complex, nice diagrams in R. Like some of these were really kind of interesting. She wrote all the code. So if nothing else, learning R can be worthwhile just for building really nice visualizations of data for your papers. So I only have about 20 minutes, but I think the biggest thing we need to get through for tomorrow is I need everybody to have R and RStudio installed on their laptops. If you do not have R or RStudio, could you raise your hand? Oh, everybody has it? Yay. Oh yeah, I think Fong sent a follow-up email to the original email saying to install them. Okay, perfect. No, just the most recent one should be fine. I don't know. There is probably a version, if you go back far enough, it will not work with the software package, but I don't know what it is. If it fails, we'll update your R. That'll be the solution. Yeah, so we will download this file somewhere on your, I put it in my desktop in a folder called course, because that's where I've been putting all the stuff we generate for the course. But the important thing is just for you to put it somewhere that you know how to get to it. That's the important part. And then double click to unzip it. Okay, so I'm a certified software carpentry instructor, and software carpentry is this really neat organization, and their whole mission is to develop lesson plans to teach computing to biologists. There's software carpentry, and there's also there's a data carpentry sister organization that also has lessons specific to genomics and geospatial data. And I just like to tell people about it. They do a lot of these like 2-day workshops. It's definitely where I got the idea to do these short 1 credit hour courses instead of full semester courses, because I feel like a lot of biologists, your schedules are full during the fall and spring, and you may or may not have time to squeeze in extra classes. A lot of the curricula already are full. So if you can squeeze in like a short course or a 1 credit hour course, you're more likely, hopefully, to get a little bit of computational coursework in. And I just think they do a great job. They teach these all over the world. We'll probably be teaching one maybe over winter break in between classes this winter here at UT. So we're just gonna start down their very first lesson. And one of the things I really like about it is it's hundreds of instructors all over the world working together to try to optimize lesson plans to make them absolutely the best possible. And I like that as a powerful way to teach, right? Because sometimes I don't know if I'm explaining something the best way. And maybe I've taught the same material 2 or 3 times, but if I pull my experience with 100 other people who've taught the material, then we can build a better lesson together as a collaborative group. So that's the whole idea behind it. So we're going to start very, very briefly down this programming with R lesson. If you are trying to learn R or Python or command line, they have a whole set of lessons for all of those. And they're generally pretty easy to self-navigate. And it's all open access public materials for teaching. So if you're ever assigned to do some teaching, you can always access these materials. And if you want to become a certified instructor, they run training courses, and they basically teach you how to be a good teacher, which is something that as a graduate student, I never got. I just kind of got shoved into TA land. Good luck with that. Hope you know what you're doing. And of course I didn't. And this was the first time going through the instructor training for this is the first time I actually got real empirical science on how to teach. And so I thought it was really powerful and I really appreciated it. And I think there's a reasonably long waiting list to get into their online instructor course. But it's worth it. I thought it was really great. Okay, so we're gonna start at the top. And I'm gonna launch RStudio. How many people have used RStudio before? A lot of people. Okay, so let's go through just what is going on with RStudio. Maybe if I quit and restart it. Okay, so you should see 4 panels. Okay, like this when you first launch it. You may or may not see this panel over here. I'm gonna actually get rid of that. You can just hit the X. So it kind of looks like its own little mini desktop with different windows open. And this is a little bit similar to a terminal, but it's a little bit smarter. It actually gives you some really, really nice features. So you can kind of imagine this like a bash terminal, but it's an R terminal. So instead of typing ls or cd, you're going to type R commands. So it's kind of like we're switching from French to Spanish. We're switching languages. But it's going to be the same sort of setup where you have a prompt, you type things, you hit enter, the computer gives you some feedback, rinse, repeat. But on the right are these really nifty features, which as you're creating objects, it's going to actually put a list of them over here and tell you and give you an easy way to see what's in those variables that you're creating. And down here is this really nice help pane. So if you're trying to figure out what a function does, you can easily pull it up over here and read. It looks a lot like the manuals that we've already seen in this class, where it tells you this is a function. It has lots of parameters. If you keep scrolling down, it's going to give you lots of information about each of those parameters. So I like RStudio as just a nice interface to kind of keep everything neat and tidy and keep all that information in one place. So I'm going to have to, I never figured out how to set this up so I could see all of the screens at once. Let me see if I can do that. Okay, so the first thing that we are going to do is set up our working directory. So if you type get wd and hit enter, it is pointed to a directory. So this is kind of equivalent in Bash like CDing to a location. Instead of changing directories, we're gonna be able to set this to point to a directory that we're interested in. And I have the material in desktop course data. So I'm gonna do set working directory users stato desktop course data. And now if I type get working directory, it should be a new location. So everybody try to figure out where you downloaded that file from the course website and point your working directory for R to that location. If you're having trouble with that, feel free to throw up a red sticky and someone will come help you. I can never figure out the paths on Windows. So if you can't either, I totally understand. We'll help you get it figured out. Yeah, you can also use the tilde. Oh, said. I happen to know that user/user/Moscato is my home directory. Don't know how consistent that is for Windows machines. So you'll know that it's pointing to the right file location if this next command works. So if you type that command, and I'll scroll up so you can see it, you should see a bunch of data scroll across your screen. That's the command, which I think highlighting it makes it harder to read. So I'm not going to do that. If you can't find the directory, we're actually probably not going to get far enough in this lesson for that to matter before class ends. So no big deal. You come in a few minutes early tomorrow, and we can figure it out. I'm going to skip over some of these various exercises and nuances. Again, if you're trying to learn R, it's a great lesson to go through. But for our purposes, for running DEC2, we're only going to just need to know a little tiny bit about R. So I mentioned having a variable earlier. In R, we can assign things to a variable using this handy arrow operator. So here's the illustration from the material. Basically, we have created a little tag called weight_kg, and that tag is pointing to a value. So if I type weight kg, say, hey, what's in that variable? The computer says 55, that's what's in that variable. And I can change that value by assigning it a new value. So I can assign it 56. And you'll notice that as you create variables and assign them values, they appear up here on the upper right part of your screen. So this is just a nice way to keep track of what you've created and what's happening. And again, if I ask the computer, what does weight kg currently hold? It holds 56. Oh, is the red really hard to see? I must have changed this. Let's see if I can. Okay.
Check everything.
Oh, I have to make this bigger. That's the problem. Yeah, okay. Let's see. I don't know if there should be a... Okay. Okay, I'm gonna quit and restart. No.
Go back there. 'Cause that's the text editor. One of those edit things.
That was mom. Yeah, I don't think that's gonna work.
Try one of these.
All right, that should be a little easier to see. Maybe. So we can do math with this. So we can say weight kg times 2.2, and it's going to calculate the answer for us. It's generally, like I talked about, naming folders and files in an intelligent, like, give yourself as much information as possible. Same is true for variables. If you name a variable W, you may forget that it's supposed to be weight. So it's extra typing, but if you name it weight_kg, that gives you a lot more information about what the variable is. So that's really helpful. We can take the results of a calculation and store it in a new variable. So you can see that created a new variable called weight pound, and that holds the results of our computation. And if we type weight pound on the command line, see what's in it, it has 123.2 as the value. So it's important to note that these two variables are not linked by that formula. We calculated it, the value got stored in weight pound. That formula is not being remembered. So let's say I change weight kg to 10. That is going to change weight kg. It does not change weight pound. So if we wanted to recalculate weight pound, we'd have to rerun that same formula. Up arrow should work. So in this case, I reran the calculation. It assigned a new value to weight pound. I don't care about printing with parentheses. Okay, how many people were able to actually read the CSV file when we tried it earlier? Okay, most of you, great. So let's play with that for just a few minutes. Let me get that back, read CSV. Oh, I have to reset my working directory because I quit RStudio and then I reopened it and forgot. What did I call here? I called it course data. Okay. So hopefully, it sounds like most of you guys already have had this read CSV working. So this is kind of like working on the command line that we were doing earlier, where we read the file in and it spit it out straight to the terminal. But what we can do in R is we can now put all of this information into a variable. And the way we're going to do that is we're going to basically take that entire thing and assign it back to a variable that I'm going to name dat, like that. So in this case, it doesn't give us any feedback on the terminal, but it does show you that you now have a piece of data that has 60 observations of 40 variables. So it read that information in and it stored it with a tag called dat. In this case, this is a data frame, which is the bread and butter of working with R. Data frames are just like Excel spreadsheets. You've got columns and rows. One shared command between R and bash is head. So in this case, when I do head dat, it gives me the first 10 rows. It wraps around because there's so many columns, but that's the first, well, I guess actually the first 7 rows. So just a little glimpse of the top of the file. There are other types of objects in R, not just data frames. If you're working with something and you don't know what it is, you can ask for the class. So you put the variable name dat inside the class function and it returns and it tells you that it's a data frame. There's also a function called dim for dimensions. And that is going to tell you the dimensions of your data frame. 60 by 40. You can use, looks kind of like matrix algebra or matrix math, but you can ask for pieces of the data frame. So if I ask for 1, 1, that is the first row, the first column. So this is very much like being in Excel and selecting a single cell in that huge Excel spreadsheet. And that corresponds with row 1, column 1 was a 0 right there. And we ask for row 1, column 1, it's a 0. In this case, you just kind of have to memorize that it's row then column. It's always row then column in these brackets. So we can ask for a different cell, row 30, column 20, and it's going to give us whatever was in that cell. We can select more than 1 row or column. So this would be like if you took your mouse and highlighted a whole little box of cells in your Excel spreadsheet. So we're going to use a function called C, which stands for combine, and pick columns 10 to 20 from rows 1, 3, and 5. That. So rows are first. So put 1, 3, 5. Columns are next. I'm going to do 10, 20. And it has gone in and subsetted rows 1, 3, and 5, columns 10 and 20, and return that to you. We can also get ranges to indicate you want 1 through 5 or 1 through 10. You can use a colon. This is saying I want rows 1 through 4 and columns 1 through 10. So again, I don't expect you guys to become R experts in this course, but I basically just want to go through a few little commands just so you can get used to the RStudio interface, see how to upload some data. Once we get into processing everything with DESeq2 tomorrow, we're going to follow very closely the DESeq2 manual. For the most part, you don't need to be an R guru to use DESeq2. The manual is really detailed. It's going to tell you exactly what to type on the command line. There's just a few little things at the beginning. You've got to get your data loaded, and you've got to get your samples labeled the correct way with the right factors. So there's like just this very little part at the beginning where you kind of have to know how to create a data frame and have values. But after that, you really don't have to know much about the innards of R. It's more about running the DEC commands, very much like we did with the bash terminal. Just understanding the commands, changing the parts of the command so that they're relevant to your experiment. So that's all we're going to do today with R. We'll pick up tomorrow with DESeq2 and finally get to the end of this long pipeline. If you guys want to stay, if you have any questions about R, just let me know. Thanks. Oh, and I forgot what the homework was today. Did I have a homework on there? What was it? Okay. Okay, yeah, I didn't update that. Yeah, don't send me that. Take a screenshot of your RStudio and send that to me just to show me you got R working, and we'll call that a successful day. Thanks, guys. And I'll update the homepage right now.